Welcome to my presentation on geothermal energy, one of our paths to a sustainable future here in the United States and across the world. For those listening, this presentation would be for my high school students, and this would come after their learning on the laws of thermodynamics. So we'll start by, also I'd like to mention that this presentation is done with an iPad app. And if you'd like some information on this, just email me or put it in our discussion forum, and I'll send you the information for it. So, what is geothermal energy? So the word geothermal comes from the Greek words geo, meaning earth, and therm or therme, heat. So geothermal energy is heat from within the earth. Now, we can recover this heat as steam or hot water and use it to heat buildings or to generate electricity. It's been used for a long, long time. It can be harnessed from the Earth's natural heat that's usually associated with active volcanoes or geologically young inactive volcanoes that are still giving off heat deep in Earth. Now, steam from high temperature geothermal fluids can be used to drive turbines and generate electrical power, while lower temperature water provide hot water for space heating purposes, heats for greenhouses, industrial uses. You can find this heated water at hot springs. It flows out of geysers. They find it at resorts and spas. For example, geothermal heat warms more than 70% of the homes in Iceland, and the geysers geothermal field in Northern California produces enough electricity to meet the power demands of San Francisco entirely. In addition to being an energy resource, some geothermal waters also contain sulfur, gold, silver, mercury, and these things can be recovered as a byproduct of the energy production. So there's a dual use to this. Not only can we gain electricity and heat energy, we can get these products as well for other uses. So where does this energy come from? Well, it comes from Earth's interior. So like the sun, it provides heat from nature. This heat, this geothermal energy, yields warmth and power that we can use without polluting our environment. So geothermal heat originates from Earth's original consolidation of dust and gas over 4 billion years ago. At Earth's core, which is around 4,000 miles deep, temperatures can reach over 9,000 degrees Fahrenheit, which is comparable to temperatures found on the surface of the sun. So much of the energy comes from elements that are still decaying. So radioactive decay, this process generates heat, it's released, and also some of this energy is leftover heat from the formation of the Earth. So how, if this heat is produced so deep down within Earth, how does it get up to Earth's surface? Well, let's look at this diagram I have here on the left, and what we see here is a model of the Earth with the core, inner and outer, the mantle, and all the way up to our crust. Now what happens is the heat from Earth's core continuously flows outward. So heat's being transferred, conducted from the core to the surrounding layer of rock in the mantle. When the temperatures and pressures become high enough, some of that mantle rock will melt, becoming magma. Then because magma is lighter or less dense than the surrounding rock, the magma will rise and it will convect and it moves slowly up towards the Earth's crust, and it carries this heat with it from below. A little bit of earth science here. Sometimes this hot magma will reach all the way to the surface, and we know that magma now is lava once it hits the atmosphere. But most often the magma remains below Earth's crust, heating nearby rock and water, and that water comes from rainwater that is seeped down through pores in the ground. Also, some of this water gets down deep through the process of plate tectonics, where ocean water is forced down below through the process of subduction. So this water can sometimes reach temperatures around 700 degrees Fahrenheit. Now, some of this hot geothermal water travels back up through faults and cracks and reaches Earth's surface as hot springs or geysers. Now, let's look at the geothermal reservoir diagram on the right. So, this natural collection of hot water is called a geothermal reservoir. And as we see down in the bottom, that red there, that's going to be our hot magma. Water will seep down through rain and, like I mentioned before, through the process of subduction. And this water gets hot, and it will begin to rise a little bit. Sometimes it's stored in these reservoirs for long periods of time. So the question now is, how do we provide electricity? How do we generate electricity using this geothermal energy? In geothermal power plants, steam, heat or hot water from the reservoirs provides the force that spins a turbine generators, and then it produces electricity. After this is used, the geothermal water is then returned down in through what's called an injection well back into the reservoir. It gets reheated. It helps maintain its pressure, and it also sustains the reservoir, because if you don't sustain a reservoir, and this would be for another class, if you don't sustain the reservoir, the land could subside, and it could cause all kinds of problems. Now, there's three kinds of geothermal power plants. And the kind that we're going to build depends a lot on the temperatures and pressures of the reservoir itself. So we're first going to talk here on slide 4 about what's called a dry steam reservoir. Now, this reservoir, very, very hot fluid, very, very hot water. It produces a lot of steam, but very little water comes through. So this steam is piped directly into what's called a dry steam power plant, and provides the force that spins the turbine generator. Now, the largest dry steam field in the world is the geysers, and this is about 90 miles north of San Francisco. And the production of electricity started at the geysers in 1960, and it's become the most successful alternative energy project in history, certainly in our nation, and it's an amazing place. You can see that tiny little picture I put there on the left. This is a picture of them producing power at the geysers. Now, another type of geothermal power plant is called a flash power plant. Okay, and this is a reservoir that produces mostly hot water. So it's a hot water reservoir. Now, this water can range in temperatures from 300 to 700 degrees Fahrenheit. And it's brought to the surface through the production well, where once it's released from the pressure of the deep reservoir, some of the water flashes or changes directly into steam in a separator. And then the steam then powers the turbines. Okay, so what happens here is this hot water comes up, and if we look in the picture here I have on the right, we have the production well. It is pulling water up, and as it's pulled up into this what's called the flash tank, okay, the pressure decreases greatly, and this causes this superheated water to vaporize, turn into a water vapor, and the water vapor is thrown into a separate tank there, and that steam produced there spins that turbine, which of course causes the generator to produce electricity. Let me turn the... Now, reservoirs that have temperatures between 250 and 360 degrees Fahrenheit, the water is not quite hot enough to flash, but it can still be used to produce electricity. And this is called a binary power plant. A binary power plant. Now, in this binary system, the geothermal water, it gets passed through what's called a heat exchanger, where its heat is transferred into a second binary liquid. And an example of this is called isopentane. It has a very, very low boiling point. And so it has a much lower boiling point than water does. So when heated, this binary fluid, flashes into vapor, which, like steam, expands across this well, and it spins a turbine, which allows the generator to create electricity. Okay, and what happens then is The vapor then the water gets recondensed into a liquid and it's reused. I'm sorry, the vapor from the secondary fluid, it's recondensed into a liquid and it's reused repeatedly. Okay? And this is called actually a closed loop cycle, so there's no emissions into the air, and that's a great thing. So let's again look at the image I have here on the right, and we see the production well where hot water from the reservoir is being pulled up, and we see the water now, instead of going directly up into to where the turbine is, it goes through this heat exchanger, and there's a separate pipe that is carrying this binary fluid, like the isopentane I just mentioned. And so as the heat is exchanged from the hot water pipe to the pipe carrying the binary fluid, that binary fluid with a very low boiling point will flash, it will become steam, it will become a vapor, go up, spin that turbine, create electricity. Okay, and again, it's closed loop, so this isopentane and all these other kinds of refrigerants, fluids that they use that have very low boiling points, which are very toxic, they're closed loops. So these chemicals do not get into our environment. So it is much safer than some of our current forms of energy. So, how do we explain all this? How do we explain how geothermal fluids can create energy for us? So we can use the laws of thermodynamics to explain how we use this internal heat for energy production. So you have a task now. We have already spoken about the laws of thermodynamics, okay? And what you're going to do is match each of the laws you've learned about with the appropriate parts of the process. And what I want you to do is log into your Glogster account and create a visual about this to share with the class. Okay, create a visual to share with the class. So I will briefly go over these laws, and your job is to you can take these images off the PowerPoint, you can take images you find on the internet as long as you give appropriate credit to where the image came from, and put it in your Glogster account. So, this image here I got from NASA. It talks first about the zeroth law. And we only talked briefly about this, but so what this law states is that if two bodies are in thermal equilibrium with a third body, then they are in equilibrium with each other. And here, in the case of geothermal energy, this can be used to explain the process of the vaporization of that secondary or binary fluid, like the isopentane I mentioned. So the water and the secondary fluid are not in thermal equilibrium at first. So anything in contact with them will be at a different temperature. So heat's going to flow from the hot water to the binary fluid until they come into equilibrium. And then, as I mentioned on 2 slides ago, at this point, that binary fluid that has a very, very low boiling point will flash into a vapor and spin that turbine. Now, the first law of thermodynamics, as you learn, this states that the internal energy of a system will increase if heat is added and decrease if work is done by the system. We can also say this law is like the conservation of the internal energy of that system. So in the case of geothermal energy, heat is added to the system of the binary liquid, that secondary liquid, and the turbine by temperature differences between the liquid and the water. So if heat is added, the internal energy of the system must either increase or it must be offset by work being done. So thus the turbine will provide the work done by the system. So E equals Q minus W will be satisfied and energy is conserved. And finally, the second law of thermodynamics, and again this image is from NASA, it states that if a process happens in a closed system, like what we're talking about, the entropy of that system increases for an irreversible process. So if the process is reversible, the entropy is constant. Now for any process in a closed system, the entropy never decreases. In the case of geothermal energy, we can assume that the system between the ground, the chamber, the mixing chamber, and the turbine is a closed system. This can be assumed because the process of pumping up the water and returning it to the earth requires quite a bit of energy, and it can't be regained. Now, if this were not the case, geothermal energy production would be a perpetual system and would be much wider spread. But of course, that isn't the case. So, where do we get this? Where in the world do we produce geothermal energy? Um, most for electricity and direct use, reservoirs that are close enough to the surface and that can be reached by drilling can occur in places where these geologic processes have allowed magma to rise up near the crust, near the surface, to where it flows out as lava. The crust of the earth is made of huge plates, and I'm sure you've had this in an earth science class before. And these are in very constant but very slow motion relative to one another. They're either grinding past each other, moving towards each other, or away. Now, at these places, especially what are called divergent boundaries, where plates move away, and convergent boundaries, where plates come together, this magma reaches the surface in these areas. So where these large oceanic plates collide or slide past each other, called a subduction zone. And the best example of these is in a region called the Ring of Fire. And on the image here, I'm going to outline the Ring of Fire for you. Okay, so if you look, I have a little highlighter moving around what's called the Ring of Fire. And this area right here is extremely volcanically active. Okay, however, much of it is underwater. Again, we see the Ring of Fire. I'm tracing a path around it. And so a lot of geothermal energy can be created in these places because of all the heat. So the areas bordering the Pacific Ocean, as you see there, the South American Andes, Central America, Mexico, in the United States, the Cascade Range, where we have a number of volcanoes on the west coast. In Canada, in Alaska, up here, this is the Aleutian Islands, and so this range right here is very volcanically active. In the Philippines and Indonesia, all these South Pacific countries and island states, and also over in the area of New Zealand. Now, spreading centers, places where plates move apart, are also geologically or volcanically active. And so right here, we have the Mid-Atlantic Ridge, we have the East Pacific Rise. So all these areas, these spreading centers, they're extremely volcanically active, a lot of heat near the surface. And we have another place, something else, another phenomenon called the hotspot. Scientists are still trying to figure out what hotspots actually are, how they occur, but there are many. One notable hotspot is right here in the U.S. This is Montana, Wyoming region, and we have the Yellowstone National Park, a very large hotspot there. On the Mid-Atlantic Ridge, we have Iceland, which is a hotspot. We have some hotspots in other locations as well. So again, they're volcanically active. There's a lot of heat near the surface. We can drill into that. If there is water there, water and steam, we can pull that up into our power plant. If there's not, there's another process that we're not going to get into where they actually have just heated rock and they pump water down to get heated to be forced back up to the surface. So these are all places where geothermal energy can be created. Now, something to note, there's something else we can do without having this immense amount of heat. We can use geothermal heat pumps. Okay, geothermal heat pump. And what a geothermal heat pump does is it can warm and cool your house in the summer or the winter. Now, these can be used almost worldwide. The Earth's temperature just a few feet below the ground is relatively constant anywhere in the world, okay? Between about 45 and 58 degrees Fahrenheit. But the air temperature can change to extremes in the summer and winter. Now, unlike the other kinds of geothermal heat, these aren't dependent on plate tectonics, right? They're not dependent on magma being near the surface. So these can be used to help heat and cool your homes anywhere, all right? It's used all the time. It needs to be used more, in my opinion, but it can be used for space heating in your home. It can be used for air conditioning in the summer. Industries use it. It can help you dry out materials for business. They use it in greenhouses. They use it for aquaculture, which is raising fish for food. They use it for heating water in your home. If you go to resorts, sometimes resorts will use these heat pumps, using this energy from the earth to heat their pools. You can use it to melt snow, and the list goes on and on and on. So how does it work? All right, how does this actually work? So you have to again tap into the ground. So here we have this image from that I got from a website of an organization that installs heat pumps, the Delta Montrose Electric Association. And so what we see here is a home, and in the bottom left, it explains how it works. So a geothermal heat exchanger system consists of an indoor heat pump, okay, a ground loop, and a flow center to connect the indoor and outdoor equipment. So right here, we have our heat pump and exchanger right here, okay, and these pipes are carrying water, all right, to and from the home. So we can, and then we have vents from the heat pump exchanger that lead to the house. They're going to carry that warm or cooler air. So these ground loop systems use constant temperature of the ground or the water several feet underground. And the pump circulates this fluid. Again, probably not the fluid I was mentioning earlier, but a fluid which can stay relatively warm year-round. So in winter, it can draw warmer fluid into the house, and in summer, it can take the fluid out of the house to cool the house off. And this can give you the installation of this. I was looking through it. It has a high upfront cost, so it's fairly expensive to put in to your home. However, it's going to save you thousands upon thousands of dollars in the life of your home. And you know, for you young people, this doesn't matter, but this will also increase your property value. So if your home has one of these geothermal heating systems, or this heat pump, it's going to increase your property value. Okay. So what I'd like you to do is I'd like you to research the advantages and disadvantages of generating electricity or heat energy from geothermal sources. I posted a graphic organizer on my Google Drive. I've shared it with you with the link you see below. I want you to remember, when you open this up, make a copy of this and put your name in the title, and then share it with me. Okay, you don't have to share it with everybody, but share it with me. You get this done, and I'll grade it on the Google Drive account. That's assignment number 2. And finally, your final project for this part of the unit is you must complete a project and present it to class. Now, the project can be a laboratory-style activity. It can be a paper, if you'd like to write a paper. It can be a website or any other mode of delivery you wish. But you must get approval before starting your project. Now, some lab activities, so you know, must be done under my direct supervision. Some others are fine to do at home or on your own. And if you choose to do something that's a little more dangerous, and you do it on your own and not under my supervision, you're going to lose your points for the project. And then you must have a parent-principal-teacher conference about your indiscretion. So keep that in mind. All right. For the project, which is specifically for the laboratory-style activity, you can click this link, and this is where the project rubric can be accessed. You have other rubrics from other projects for the paper, the website, and other things. I'm going to give you a couple projects you can use. First project, what factors affect the heat transfer from rock to water? In this, it shows you your objectives, the equipment you will need, all of the equipment I have, safeties, precautions, and then some suggestions to help you out with this. Project 2, how is energy transferred between fluids in a binary geothermal power plant? How does this work? Okay, so read through this. If you like it, ask, and we can. So here's some other options. You can make a model of a geothermal power plant. You can make a model of a working geyser. Make a model of a steam turbine. If you'd like to write a paper or write an article, maybe a website, answer questions like these: What effect does water or steam pressure have on geothermal energy production? What are the social and economic implications of putting a power plant near a hot spring, which are often developed at tourist areas? what type of geothermal system would be most appropriate for your state, your town, your school, your home. What savings in electricity and dollars could a geothermal system provide to your community? And here were my resources. All of these resources you can also access for your paper, for your project. And some of the lab activities, the two that I described, I adapted them from a U.S. Department of Energy paper. It was authored by Laura Butterfield and Dr. Brandon Gillette, and also Richard Shin. Thank you for listening to my presentation.